All right, ladies and gentlemen, this is the final video for thermodynamics on the relationship between delta G and K. So our last big topic, and by the way, this is why we have to do thermodynamics after equilibrium, because we have a relationship between the two. So big point, delta G and equilibrium, they're related. They are not the same thing, but they are definitely related to one another. So first up, how does delta G indicate if a reaction occurs? Well, we know this, right? We know how delta G indicates if a reaction occurs. If delta G is negative, then that means that we have a spontaneous reaction. But think about direction. When we say spontaneous reaction, what direction are we talking about? What we're really talking about is in the forward direction, right? That's what we mean, right? The forward reaction, the reaction as written, is spontaneous in the forward direction. And if delta G is positive, then that means that it's non-spontaneous. But again, in what direction? It means in the forward direction. The reaction as written, left to right, is non-spontaneous. It does not occur on its own. So if delta G is negative, just going back to this, it means that the forward reaction occurs on its own without any outside intervention. Well, if you have a non-spontaneous reaction, obviously it's non-spontaneous in the forward reaction, but what does that mean about which reaction will occur on its own? Well, we know that means that the forward reaction will not occur on its own. But what that's also saying is that the reverse reaction must be spontaneous, right? If the forward reaction is non-spontaneous, then the reverse reaction must be spontaneous. So in this one, we can also add, so if delta G is positive, then the reverse reaction occurs on its own. And then likewise, we have K. How does K describe a reaction? Because we know that K tells us things. And remember, K is the concentration of products over the concentration of reactants at equilibrium. And we talked about this a number of times in the equilibrium unit. If K tells us by its magnitude information about the reaction. If K is greater than 1, if K is greater than 1, what does that mean? It means that we have more products than reactants at equilibrium. Right, just flat out, that's what it means. And if K is less than 1, then the opposite is true. We must have more reactants than products at equilibrium. Right, the magnitude of K in reference to 1 gives us information about which thing we have more of. Well, okay, here's the thing. These two statements, the statements about the sign on delta G and the magnitude of K, they're actually very intimately related to one another. If K is greater than 1, you have more products than reactants at equilibrium. Okay, so which reaction, the forward or the reverse reaction, must have occurred in order to get to equilibrium? Well, if you end up with more products than reactants at equilibrium, then you must have had the forward reaction occurring on its own without any outside intervention, because that's how you're going to wind up with more products than reactants, if the reaction proceeds in the forward direction. So if K is greater than 1, so the forward reaction occurs more frequently before we get to equilibrium. I mean, they're both occurring at equilibrium at the exact same rate, but the only way to wind up with more products than reactants is if your forward reaction was happening more frequently before you got to equilibrium. Likewise, if K is less than 1, well, that means that you have more reactants than products. Okay, so which reaction must have been occurring more before you got to equilibrium? Well, if K is less than 1, then you must have had the reverse reaction occurring more frequently before equilibrium. And now suddenly look at what we're saying here. We have this statement about K being greater than 1 talking about the forward reaction occurring on its own, which, oh goodness, oh my goodness, delta G being negative is saying the exact same thing. And likewise, if K is less than 1, then the reverse reaction must have been occurring on its own, which, oh hey, look, delta G is positive. That is saying the exact same thing. So huge star circle around this idea. The sign on delta G and the magnitude of K are basically saying the same thing about a reaction in slightly different terms. Delta G is saying before you get to equilibrium, which reaction is going to occur more frequently, forward or reverse. And then K is saying, okay, well, now that reaction has occurred, now on its own, we can make a statement about relative quantities of products and reactants. But you will never, ever have a reaction that has a delta G negative sign having a K value that is less than 1. Every time you're going to have a delta G that's negative for a reaction, its K value guaranteed is going to be greater than 1, because that means that the forward reaction is occurring on its own, so you're going to have more products than reactants when you get to equilibrium. This is an enormous point, an absolutely enormous point. Simply knowing the sign of delta G allows you to predict the relative magnitude of K. So this this graph is sort of just talking about delta G naught, but it's making an additional point about equilibrium. So delta G naught, remember, means under standard conditions. And what we're graphing here on the y-axis, we have free energy, so that's delta G. And then on the x-axis, we have increasing proportion of products. So what that means is that at this point, we have no products at all. So at this point, right, we would have pure reactants. And if you only have reactants in your chemical reaction, then what direction is the reaction going to go? Well, there is no option. Even if, no matter the reaction must go in the forward direction. And I like to think of this graph because it looks like a valley, right? It looks like this landscape that's got a big dip in the middle. And it's kind of like saying that if you start with a boulder up there where it's pure reactants and you let go, there's truly only one direction that that boulder can go. It has to go in the forward direction. So like here, if we're starting with nothing but pure reactants, delta G is negative. The forward reaction is the one that is going to occur spontaneously. It's going to occur on its own. It's going to go forward. But, right, direction of spontaneous reaction, we're going forward. Likewise, if we consider like all the way over here, if you start with nothing but pure products now, and again, products are on the right, reactants are on the left. So reactant is not a term for what you're starting with. Reactants are the things that are on the left-hand side of your chemical reaction, and products are the things that are on the right-hand side of your chemical reaction. If you start with pure products, again, if we think of like a boulder that's sitting here, and then you let go of it, it's not going to go further to the right. No, it's going to go this way. So there's only one direction that it can go spontaneously. It's going to go in the reverse direction. So our delta G is going to be positive here. But what I want to point out is, what if our little boulder, right, gets to the middle and you were to let that boulder go? Well, it's not going to go in one direction over the other, right? It's stuck. There's no push for it to go forward or reverse. That's equilibrium. Oops, sorry. That's equilibrium. So this is the really big point. If delta G, not delta G naught, just delta G, because remember delta G naught refers to standard thermodynamic conditions, 25 degrees Celsius, 1 atmosphere pressure, 1 molar solutions. But if we've like altered the conditions, maybe we're not at standard pressure, and you have a set of circumstances where delta G is equal to 0, then we are actually right at equilibrium. There's no longer any push for one reaction to occur over the other, the forward reaction to occur over the reverse reaction. So delta G being positive or negative, it's like saying which reaction has to occur in order to get to equilibrium, and then when we're at equilibrium, now the forwarding reaction are occurring in the exact same rate, so one is not occurring more than the other. If delta G is negative, the forward reaction is favored, we're not at equilibrium. If delta G is positive, the reverse reaction is favored. So when I say that we link the signs of delta G with the magnitude of K, they're not both at equilibrium. It's like you take a reaction to start with, and what's its delta G value? Where is it going to go in order to get to equilibrium? So we do have a mathematical equation that links our delta G value and our K value, and it's delta G naught equals minus RT natural log of K. Now, this equation shows mathematically what I was talking about with the sign of delta G being linked to the magnitude of K. If delta G naught is negative, okay, if delta G naught is negative, then the natural log of K must be positive, because notice that we do have a negative value in here, right? So if this thing right here is negative, then this bit has to be positive because we have this additional minus sign in there. Well, if you're taking the natural log of something, the only way to take the natural log of something and have it wind up being a positive value is if your K value is greater than 1. So if you take the natural log of something that's greater than 1, you're going to get something that's positive, which then when you negate it in the equation, you're going to wind up with a negative value for delta G. And then likewise the reverse. If delta G naught is positive, the natural log of K must be negative, right? Because we're going to have two negatives, we've got to cancel them out. So if you take the natural log of something that is less than 1, you get a negative number, you add that second negative in, you're going to get the positive value on delta G naught. And just to comment on the R value here, so delta G is in kilojoules per mole reaction, right? We've seen that before. K has no units, right? Absolutely no units whatsoever on K. R, we have a number of different R values that are on our reference table. So which one are we going to want to use? We need to use the joule value, which is the 8.314 value, because that is the only one that has joules, right? We've got kilojoules here. But we're going to need to convert it, because very typically delta G will be in kilojoules. It'll ask for it in kilojoules, but the R value is going to be in joules. So you can keep the R as 8.314, but know when you solve and you get your value for delta G, that would then be in joules. So you're probably going to get like a really big number, and then you're going to need to probably convert that from joules back to kilojoules. Now temperature. Here, temperature must be in Kelvin because we need that absolute scale, because signs mean things in delta G and they don't mean diddly squat in temperature. They just mean, oh, okay, it's really cold. We can't have Celsius when we're working with this thing. We need an absolute temperature scale. So absolutely massive point. We have to understand both mathematically and conceptually how the sign on delta G is linked to the magnitude of K. So I think we're going to outline the problem in class together, and we're just going to talk about how we could get the value for K for this reaction from the information that's in Appendix 4. So the final thing, just a comment about delta G. Delta G naught, remember, it means whether a process is thermodynamically favored. Meaning, will the forward or reverse reaction occur on its own? That's what delta G naught is saying. It is not in any way, shape, or form concerned with how fast a reaction is occurring. No. That's kinetics. Remember, there is absolutely no relationship between whether a reaction occurs on its own and whether or not it occurs quickly. Those are not the same things. I know in our little heads that we think that those are the same things, but they are absolutely not. The Grand Canyon forming is a thermodynamically favorable process. Did it occur quickly? No, it did not. So we have to separate this idea of a reaction occurring on its own with a reaction occurring quickly. They are not identical. They are, in fact, no way related to one another. Not at all. So this is a question that the AP actually likes to ask. They like to give you all this information about a problem and then say, oh, okay, so we put the stuff together in a beaker and then we didn't observe anything. Saw nothing. Why? Right, and ask you, okay, so we know that the delta G value is negative. Put it together, didn't see anything. And they say, okay, well, what's up? And I guarantee you the first thing that you're going to want to say is, oh, is that the wrong temperature? No, they told you the delta G value was negative. That means at that temperature. It means that at that temperature, the reaction is thermodynamically favorable. So no, the reason cannot be that it's at the wrong temperature. It is in fact at the absolute correct temperature. So you cannot think thermodynamically about this. This is not a thermodynamics question. This is a kinetics question. So we want to answer in terms of kinetics, right? Why aren't you seeing a reaction happen even though you know it's thermodynamically favorable? That means that you're not allowed to talk about anything related to thermodynamics. No delta G, no delta H, no delta S, and certainly no temperature. But what you could say is, okay, maybe it's a really long process. Maybe it takes a really long time. Another explanation, maybe it has an incredibly high activation energy, right? Because remember, kinetics is all about that potential energy diagram curve, right, where you've got this big hump in the middle. Maybe it's got an enormous activation energy. Maybe you need a catalyst of some kind, right? Maybe there's a reason why it's not occurring instantaneously. Maybe that's a kinetics issue. But you do not want to say that it's at the wrong temperature, because it is at the right temperature. It is absolutely at the correct temperature. So you have to think kinetically about, okay, why isn't this reaction occurring immediately? That's kinetics. We know it's thermodynamically favored. We know it's going to happen on its own. Maybe it just takes a while. Maybe it needs something else to get the reaction going.